Hello, everyone. Welcome to the April 6th edition of Math 135. Quick reminder, your project updates are due on Thursday, and you're going to need 100 survey responses. On Wednesday, we'll be spending the class primarily on working on your updates, so let me know if you have any questions about that. So up to this point, when we've been estimating things such as the sample average number of hours students spend on TikTok each week, or the average number of children in a family that sends one of their kids to Lee, we've used confidence intervals to estimate what is the sample, what does the true population mean? What range of values are we relatively confident the mean falls between? So today we're going to switch to a different topic, which is the topic of hypothesis testing. So I want you to take a second and think about the following. You are looking at a bunch of numbers that are in people's tax returns. And you want to know, okay, so for the numbers that appear in the tax returns, what digits do you think should most frequently appear as the first digit of the numbers in the tax returns? What is the distribution? Does the number 1 appear 1/9 of the time? What about the number 2, 3, 4, 5, 6, 7, 8, 9? Think for a second and try to guess what percent of the time does the leading digit of a number in a tax return start with a 1, 2, 3, 4, 5, 6, 7, 8, or 9? Well, if you thought that they should appear with roughly even probability, you could be forgiven because that's what you might expect. You might expect that the leading digit should be a 1, a 2, a 3, or 4, or 5, equal amounts of the time. However, if you thought that, you would be very wrong. So this is what's called Binford's Law. Binford's Law is something that was observed by Ted Hill, and what he observed, well, sorry, it was by Binford, but Ted Hill also showed why this is true. He observed that the leading digit of things in government records, population studies, tax returns, are much more likely to begin with a 1 than they are with a 9. Very few numbers begin with a 9 in data such as this. So why would we care about this? Well, let's say you're an accountant and you're a forensic accountant. One of my friend's little brothers is a forensic accountant. And when someone cooks their books, they might not be aware of Binford's Law, and they might use a distribution of numbers where the first digit does not align in frequency with what we see from Binford's Law. They might have numbers that start with 4 or 5 too much of the time. Now, it could be true that they are telling the truth. However, we need a way of analyzing how likely is it that someone would get such a distribution of leading digits. And if it's not very likely, you might be inclined to think that someone was lying. So this is the domain of hypothesis testing. Every hypothesis test begins with something called the null hypothesis. This is the statement of no change. For example, when you are investigating someone's books as an accountant, the null hypothesis is that the person is telling the truth. Their numbers are legitimate. How much evidence would you need to not believe that anymore? Well, the alternate hypothesis, H1, sometimes called the alternative hypothesis, is the hypothesis that is in opposition to the null hypothesis. We're gathering data, and we want to know if our numbers give us sufficient reason to believe the alternate hypothesis over the null hypothesis. In the case of investigating someone's accounting books, the null hypothesis is that the person is telling the truth, and the alternate hypothesis is obviously that the person is lying. And how much evidence would you need? Would you need some to see that their numbers occur less than 1% of the time, 1/10 of a percent of the time, 1/100th of a percent of the time? That's the alternate hypothesis. And we need to figure out what level of evidence do we need to believe it. I'm going to give you another example of a null hypothesis versus an alternate hypothesis. Let's say you want to know, are students spending more time on TikTok now that our classes are on Zoom? So let's say we saw that the average student was spending 5 hours on TikTok each week before we went to Zoom classes. And we take a sample of students and we find that on average they're spending 7 hours on TikTok after per week now that we're on Zoom. Is that enough evidence to accept the alternative hypothesis that they're spending more time? Well, it's going to depend on a lot of factors, and these are factors that will be relevant to what we're doing. So what I want you is to practice identifying what the null hypothesis is and the alternate hypothesis. So Motor Trend is a magazine, and they say that the average time for a Ford Mustang to go from 0 to 60 miles per hour is 4.4 seconds. You want to set up a statistical test to challenge that claim of 4.4 seconds. What's the null hypothesis? I want you to take a second and identify in your notes. What is the null hypothesis? What is h0 equal to? Well, think about that for a second. And what you're probably going to identify is the null hypothesis is that the average time to go from 0 to 60 is 4.4 seconds. All right, well, that was relatively easy. The null hypothesis is the hypothesis of no change. So let's use the following situation to identify the alternate hypothesis. The town of Leadville, Colorado has an elevation of over 10,000 feet. Suppose you want to test the claim that the average time to accelerate from 0 to 60 is longer in Leadville because of less oxygen. What would you use for your alternate hypothesis? Well, recall that the null hypothesis was that mu is 4.4. What's the alternate hypothesis? Well, if you think about it for a second, I think you'll agree that the alternate hypothesis is that it takes longer than 4.4 seconds to accelerate from 0 to 60 miles per hour. And so when you look at the problem, there will be words that indicate what should be the alternate hypothesis. We're testing whether this is true compared to the null hypothesis, which was it takes 4.4 seconds still to accelerate from 0 to 60. The alternate hypothesis says, well, we think it's longer, and that's the test that you do. All right, this one's a little hard to see, so let's go and zoom out a little bit. So now we're going to do part C. Suppose you made an engine modification and you think the average time to accelerate from 0 to 60 is reduced. What's the new alternate hypothesis? Well, I think you can write down your notes. The alternate hypothesis, I'm sure that you wrote down your notes, is that it takes less time to go from 0 to 60 because you made your engine better, and therefore the car will go faster and it will take less time to go from 0 to 60. All right. So now you've got some experience identifying what's the null hypothesis and the alternate hypothesis. Now we actually have to know how to run this test. So I'm going to define some terms, and then we will see whether the tests we saw before were one tail, two tail, right tail, left tail. So a left tail test occurs whenever the alternate hypothesis is less than the value in the null hypothesis. So for example, the null hypothesis might be that the population mean is 4.4, and the alternate hypothesis might be that the mean is less than 4.4. A right tail test is something very similar, except an example might be that the mean is bigger than 4.4. And last but not least, the two-tailed test occurs when you're not sure whether it's bigger or smaller, so you just say not equal to. So those are what the tests look like: left tail, right tail, two tail. These tests get their names because of the type of probability calculation that you're going to be doing in the not so distant future. But let's go there and find out what that might look like. So we're going to go through the example of this right here. So we're going to study Anna's hummingbirds. It's a species of hummingbird in the Grand Canyon. you take a sample of 6 of these birds, you weigh them and release them, and these are the weights that you get. X is a random variable representing those weights, and we know from studying Anna's hummingbirds elsewhere that the population standard deviation of these birds is 0.7 grams, and that the mean weight is 4.4 grams. And you want to know, does the data you found indicate that the mean weight of the birds in this part of the Grand Canyon is less than 4.55 grams? So I want you to write down what is the null and alternate hypothesis. Is it a left tail, a right tail, or a two tail? Well, I'm sure that the alternate hypothesis that you wrote down was that the weight was still 4.55 grams. But the alternate hypothesis is that these hummingbirds weigh less in this part of the Grand Canyon. So if you notice, if I go back to the previous slide, you'll see that the question we were asking was, does the data indicate that the mean weight of these birds is less than 4.55 grams? And that's why our alternative test is mu less than 4.55 grams. And what is this test? Is it left tail, right tail, or two tail? Well, I think what you'll see is that this is a left tail test. Okay, that brings us to the question of what sampling distribution do we use? Well, if we go back to our previous slide, what are we doing? We know that the distribution of these birds is normal, and we're taking a sample mean. So what we need to do is we need to work with the distribution X bar. And what do we know about this? It is normal with mean 4.55 and standard deviation 0.7 over the square root of 6. Okay, so it begs the question, where is this coming from? Well, when you are looking at your test statistic, you always use the value coming from the null hypothesis. And if we go back to the previous slide, we saw that the population standard deviation was 0.7 grams. And that's where we got our standard deviation from. Oops. Okay. So we know that X bar is normal. So what we need to do is we need to do some kind of probability calculation. We're going to do this probability calculation on the whiteboard. Okay. So what do we know? Well, if we took the sample of those 6 values, we would find that our sample mean is 3.75 grams. So where does this come from? If I go back to my original data set, I see that if I average these 6 numbers here, I will get 3.75 grams. Okay, and we know that under the assumptions of the null hypothesis, X bar is normal with mean 4.55 and standard deviation 0.7 over root 6. All right, so we want to know what's the probability that X bar is less than 3.75. Basically what this is asking is, Okay, assume our null hypothesis is true. Assume the population of hummingbirds in this part of the Grand Canyon really is 4.55 grams. That's what the null hypothesis said. It said that the population mean really is 4.55 grams. If it is that big, what's the probability we got such a small sample mean? That's what we're going to calculate. And this probability is too small, we're going to not believe that. So we need to find, well, so this probability is equal to the probability that x bar minus 4.55 over 0.7 over root 6 is less than 3.75 minus 4.55 over 0.7 over root 6. And we calculate this, well, this we know is the standard normal variable. And so this tells us the probability is less than negative 2.80. That's what we should get when we calculate this quantity on the right. So let's look this up in our table. And what we find is we get a probability of 0.0026. This probability is 0.0026. That's really small. This is what we call the p-value of the test. It's the probability that we got such an extreme sample mean, assuming the null hypothesis is true. That is such a small number that it should only occur 0.0026 of the time. That's less than 1% of the time. This probability is so small that we conclude that the null hypothesis is false. And the alternate hypothesis is true. So we've rejected the null hypothesis in favor of the alternate hypothesis because the probability of getting such a small sample mean is too unlikely in the case that the null hypothesis is true. And because it's so unlikely, we decide that we just cannot believe that it's true. All right, so this is one problem, and we'll have more to do in class, but I'm just going to describe some of the other things that you're going to need to know. So the p-value we just defined, the p-value is assuming the null hypothesis is true, what's the probability that the test statistic will take on such an extreme value? Now, this is a probability you're going to calculate from the sample data, and it's a calculation that you've spent a lot of time on in chapter 7. The smaller the p-value, the stronger the evidence that the null hypothesis is not true. So a large p-value, you probably say, I'm okay with the null hypothesis. A really small p-value, you would reject the null hypothesis in favor of the alternate hypothesis. So for a left tail test, you're going to calculate the z-score just like we did today. This one is just like the one we did. We calculated this z-score, and we calculate the left tail area. That's why it's called a left tail test. And that's what our p-value is. It's that left tail area. Similarly, a right tail test has the following null and alternate hypotheses, and the p-value will be a right tail area. The two-tailed test occurs when our alternate hypothesis is that the mean is not equal to something, And what you do is you find the area in the left tail and you double it, or you find the area in the right tail and you double it. And so this will be an example of, what do you do when you don't really know initially whether what the alternate hypothesis should be. Okay. So the last thing I want to define is you can ignore the second part. We're not going to talk about that a whole lot. You can ignore this part. The significance level of a test is the cutoff for rejecting the null hypothesis. We call it the probability of a type 1 error. We're not going to worry about that too much, but it's the cutoff. And so what you say is basically if your p-value is less than alpha, we reject the null hypothesis. And if the p-value is greater than or equal to alpha, we don't reject. All right. So that's going to be summarized in just a second. But that's what we call the significance level of the test. The most common significance levels are 0.01, 0.05, and 0.1. All right. So this slide just summarizes what I just said. If the p-value is less than alpha, we reject the null hypothesis and say the data is statistically significant at the alpha level. And if the p-value is bigger than alpha, we do not reject the null hypothesis. So the basic components of a statistical test are you need to state the null and alternate hypotheses at the alpha significance level. We find the test statistic, which is, there's the sample mean for you guys, and the sampling distribution. We find the p-value, we test the conclusion, and we interpret the results. So that's what I've got for today. We'll do the next example in class. So let me know if you have any questions, and I'll see you in class.